everyone. Welcome to CAE Associates ANSYS e-learning series. This morning's topic will be on Workbench LS-Dyna. My name is Steve Hale. I'm a Senior Engineering Manager here at CAE Associates. And the web today will last approximately 30 to 40 minutes. And everyone is muted, so if you do have any questions, please just type them in the chat window, which is at the top of your screen. And you should be able to get to those questions, or at least some of the questions at the end of the webinar. Okay, let's get started. Hopefully everyone can hear me. And the topics we're going to cover today are, in addition to the Workbench LS-Dyna product, and I'll discuss what it is and some of the features that are available within the Workbench Dyna product. And then I'll go through a fairly straightforward demonstration of a copper cylinder impacting a plate, both a rigid and a flexible plate. Moving on, what is Workbench Dyna? Workbench Dyna, it's a new user environment for pre-processing, solving, and post-processing LS-Dyna models. It can power of the Dyna solver with the ease of use of the ANSYS Workbench environment. So if you're familiar with the ANSYS Workbench and particular mechanical interface and the design modeler interface, this should be fairly straightforward to pick up because the interface is the same. There are just some additional menus that are available for setting up the Dyna model. Here with Dyna, LS-Dyna is the leading commercial explicit dynamic solver. It's very robust, it's fast, and it's used for solving high-energy transient dynamic events. The applications typically include impact analysis, drop test analysis for commercial electronics, for cell phones, for computers, laptops, and so forth, crash dynamics analysis, manufacturing problems, buckles, and so forth. Workbench Dyna is the result of a collaborative effort between Liverpool Technology Corporation, and they are the developers of LS-Dyna, and ANSYS Incorporated. Workbench LS-Dyna works with version 14.5, not with any of the prior versions of Workbench. We have an image of an analysis that was done with LS-Dyna, obviously very complex, of a full vehicle crash. Moving on, the product requires an ANSYS LS-Dyna license. The utility itself is installed separately from the standard ANSYS install, and it's available from the ANSYS customer, or will be available from the ANSYS customer portal extension library at no extra cost. It's not up there yet. It hasn't been officially released, but it should be released towards the end of this month. The interface created using the newly released ANSYS customization toolkit. You may have heard of this. This is the ACT utility. And this utility enables customization of ANSYS Workbench interfaces. So you can set up your own within ANSYS Mechanical or other Workbench environments. License ACT. If you want to do any customization yourself, you could license ACT customization for a static analysis, or you can customize it to create your own menus for LS-Dyna in case there are some capabilities that are not included with this tool. Parallel processing is fully enabled, so you can use, you have the license for it, you can use parallel capabilities. If you're an advanced Dyna user, what you can do is you can write out the .k file directly, and then you can add additional commands to the keyword input file, which is the Dyna formatted input file. And at you can see another example of a Dyna analysis, which is can crush type of analysis. So it's very, the Dyna solver is very robust for this type of application where you have significant contact, very severe deformations, and high strains and plasticity. As I mentioned before, it uses the Workbench mechanical interface. So if you are familiar with that interface, it won't be too much of a stretch to learn the additional menus that are required to set up the Dyna model. Some features. There is and has been a Workbench LSDyna export tool that's been available for a couple of prior revisions of Workbench. All of those features are still available. Now, the limitation of that feature was that it didn't have an extensive pre-processing, and in addition, you couldn't do any post-processing with that tool. You had to write out the Dyna input deck, run it separately, and then post-process using the LS-Prep post-processor, not Workbench. So one of probably the biggest advantages of this new Workbench LSDyna tool is that that you can post-process within Workbench. All import capabilities are still available. All of those tools that you have within Workbench are still there. Cleanup tool there. You can parameterize the geometry, loads, properties, and results. So you can make it a fully parametric model. It has access to most of the contact features that are available within LSDyna, including bid or tied contact, frictional contact, eroding contact, single surface contacts. You can assign rigid bodies and rigid body loads. You can apply forces, so initial velocities, both translational and rotational velocities. You can set longitudinal and torsional springs and dampers. You can apply constraints, point masses, body, rigid joints between parts. It also supports most of the Dyna solid and shell formulations, many different shell formulations, for example, that you can now assign within the Workbench environment. And the 4 has a comprehensive set of post-processing tools. You don't need to learn the LS-Prep post anymore. I'll ask you a question here. I'm going to whole question and ask you whether or not, what level of experience you have with LSDyna. Have you ever used it? Have you seen it used? Do you have some experience with it, or do you use it frequently? So let me open up this poll, and I'll give you a minute to respond to that. Okay, the answers are rolling in now. Okay. Let me close the poll. Share the poll results with you. Okay. All right. So about, let me see here. Just look at percentages. 30% of you have never used it. 28% have seen it used. And a smaller percentage have some experience with it. So the majority of you have not, don't have much experience with LSDyna. Okay. Let me move on. Let me go on to the demonstration problem here. And what I have is a copper cylinder. It's 2 inches in diameter, and 2 inches long, and it's impacting a steel plate at 400 miles per hour. So it's moving pretty fast. This is essentially a Taylor bar impact test, which is used for determining yield strength of metals at impact velocities. And I'm going to solve this first with a rigid plate, then I'm going to change it to a flexible plate, and we'll see what happens. So let me up. And see what I have here is I have an engineering data component system for setting up material properties that's linked in with a Workbench LS-Dyna analysis system. Okay, the G is already set up, and some parameters that I've defined for some of the dimensions of the copper cylinder, and also for the thickness of the steel plate. Mechanical, this is what the geometry looks like. Simple. And what I want to do is when I first import the geometry, I want to define this plate as a rigid body. So I'll click on surface body, and you'll see down under the details pane, it's set to flexible. And I'm going to switch that rigid. I think rigid bodies is very useful for speeding up an analysis. So in parts where you don't need to have a stress solution or a stress solution, you can define those as bodies, and it'll speed up the solution substantially. Thickness is parameterized, so I can easily change that in the parameter manager. What I'm going to do now is I want to go back to the engineering data page and I want to set up my copper material and assign that to the cylinder. So now I just have structural steel defined. I'm going to click this library icon and access the general linear material library. And where I have a copper alloy, NL, for nonlinear, I'll just click plug. That'll add that to my engineering data library and make that for my model. So on the contents of engineering data, that table includes the copper alloy. If I copper alloy and look in the table of individual properties, you'll see that my yield strength is about 40,600 psi. I'll open that up a little bit so I can see some significant plastic deformation when it impacts. So to 30,000 psi. Trick page. So I'll go back to the mechanical interface. I'll like model, right click, and fresh material. So this is the same procedure you would use for stack analysis. Solve this cylinder body. I'll change the assignment of the material to let's see. I have to refresh the material list again. Okay, I see it there. Let me go make sure I have this set up. Okay, alloy defined. So back here, refresh the material. On structural steel, and I still see it. So what I'm going to do, I'm going to go here, and under Mold, I'm just going to right-click and refresh. Okay, now copper alloy NL available. So properly assigned to my cylinder. Let's contact definitions. Under actions, I have this item called body interactions. If it just says body interactions, now that's if if you're familiar with that, that's a single surface contact type. So that checks for contact between external surfaces of all bodies, or I should say parts, in the model. And change that to contact or to bonded contact if I want to. I'll change it to frictional and just give it a very small friction coefficient. I can use dynamic friction as well as static friction. Let me mesh. I don't have a mesh assigned here yet. Now, if I click on mesh, you notice that the physics preference is set to explicit, and that's important because it has to use lower order element types without the mid-side nodes for by using a Workbench LS-Dyna analysis type, it's going to automatically mesh these with 8-noded bricks or 4-noded TED elements. If I right-click on this and choose Generate Mesh, it's just going to create a default mesh for me. And what we see is, if we listen there, got some relatively small elements in that cylinder. And that because small elements tend to drive your time step down in explicit analysis. So we prefer a more uniform distribution of elements, fairly uniform element sizes. So to achieve that, what I'm going to do is right-click on Mesh, insert a method to my cylinder, change that method type to multi-zone, and that hex mesher. And when I read the mesh, I should get a more uniform distribution of elements, which I do. Fewer elements and the element sizes are more uniform. Okay, moving to the Workbench LSDyna analysis. I want velocity to the cylinder. So I click Conditions folder, velocity. I select cylinder. I'm going to assign the velocity of 7,000 inches per second, which is approximately 400 miles per hour. The direction, I can assign direction by picking a face. That direction normal to the face. It's not in the correct direction yet. It should be in the negative Z direction. So I switch in, and it's pointing now towards the plate. Now, the analysis system, this is where I can define the total transient time. So the end time of my analysis is going to be 3 milliseconds. So I want to put 003 in here. A unit system to British inch pound second unit system. So that's in the solver. Change the number of CPUs to use my analysis. So if I want to have a license for processing, I can increase the number of CPUs. I want the hourglass type. The default hourglass type typically is not the best choice. So what I can do is switch this down to any of the available Dyna hourglass control types. Use the viscous exact volume integration or volume Flanagan-Belichko type. And I can use the hourglass coefficient if I wanted to, but I'll take the default here. Output controls, I can specify how many output points to write to the results file. I click on Calculate Results to Pro Control. I can change it to equally spaced points, and right now it's set to 20. Now, 20 isn't really a lot of points. It will give a very good definition of the results. So I typically increase that number, and I'll choose 80. That'll give me 8 result sets, results files. Okay. I have my initial velocity defined. I have my analysis settings defined. So I want to fully constrain this rigid plate. Click on Workbench LS-Dyna, and I'll insert rigid body constraint. I'm going to put the plate, apply plate, and by default, all of the rotational directions are fixed. And I could up if I wanted to. Now, the thing I want to do is I want to make this a little more interesting. And to do that, I'm going to open impulse load to the very top of this cylinder in the X direction, so in the transverse direction. That's going to cause this cylinder to rotate a little bit before it impacts. It tilts as it's traveling towards the plate. Right-click, insert force. I'm going to force to top face the cylinder. Change the define to components because I want to define this in the global X direction. There's a down at the bottom that I can modify. What I'm going to set up load. Impulse load is going to go from 0 pounds and back to 0 in 0.0001 seconds. So you'll see the graph of that impulse load here on at the bottom. It shows singular impulse load. And now we're ready to solve the analysis. What I do is insert some results. So I'll insert deformation, total deformation. I'm going to insert a use result, and this is required for plastic strains. So if you want to look at plastic strains, at the moment, the way this is set up is you have to insert a user-defined result, and the expression is EPS. I want to track energy data, and to do, I go up to the menu near the top, and I can extract information from a variety of ASCII files that get written from the Dyna analysis. And one of the most common ones to look at is this global data result file. So if I pull data, what I can do is I can graph. This allows me to graph energy data from the analysis. So I could pick like global kinetic energy, global internal energy, mass energy. Let me use those three and click apply. Solve this. So I right-click, and this solves pretty quickly. So it's seconds of transient time, and it calculates the time steps for you based on the wave speed, the elastic wave speed through each of the parts. Take a look at these results now. Look at the plastic strain result. That's about the most interesting result we have. I can make this time. So you see that the cylinder impacts the rigid plate, bounce off, and we get a significant amount of plastic deformation. If we look at the contour bar, we have 61% peak plastic strain in here. Dynamically rotate this while it's animating. Look at, let me stop the animation. I'll graph the energy data that I requested. And so this is a graph of kinetic energy in gray. And then the green line is internal energy. So once it impacts, the vast majority of the energy gets transferred to internal strain energy in the cylinder, in the copper cylinder. And then I have hourglass energy as well. is something you typically want to track to make sure that you don't get too hourglassing in the elements. So, that energy we see there is pretty small. Okay, that's our first case. What I want to do next is I want to change this plate to a flexible plate. So I switch this, click on this body, and change the stiffness behavior down here from rigid to flexible. Notice down here that under Workbench LSDyna, the rigid constraint item has a question mark next to it. I don't have any more rigid bodies in my model. So I want to press that and strain the right side, the right edge of this plate. So right insert, fix support, change to edge select. I'll pick that edge, click apply. Now that it's fully constrained. The thing I want to do is I want to track the reaction forces. I have a fixed constraint here. I can click ASCII output, reaction forces, and I'm going to bring up a reaction force item under solution, and I select that fixed support boundary condition, and it will grab reaction forces at that constraint location. Let me again. And again, this will solve quite quickly. Extract results from the results files. And I have now look at the plot of plastic strain. I can't see cylinder anymore. That's because it's bounced off to the left. So let's take a look at the animation and see what's happening here. Let me move a little bit. So you can see that there's quite a bit of flexibility in the plate. It's quite a lot. And it actually back and hits the cylinder a second time and creates a secondary dent in that cylinder. What I got to mention is you look at this from the side as trying to slow this a little bit. Slow that down. There we go. You can see as the cylinder comes in, it starts to rotate the global y-axis, and that's because we have that transverse impulse load. Okay. What I want to hear for the project page, and if you look under the parameter manager, I have a couple of design points set up. The one that's solving so far is for the case where we have a 2-inch diameter cylinder and a 2-inch long cylinder with a 0.2-inch thick plate. Design point, actually design point 1, which has a 3-inch long cylinder, 2-inch diameter cylinder, and a 0.25-inch plate. So what I can do is I can right-click on that design point, copy inputs to current to project page, and click Date Project. And that's going to update my geometry and resolve. Now, if I click on Mechanical again, which is you'll see the geometry will get updated. So the geometry's been updated now. It's going to and solve. It's remeasured. And again, Program Manager allows you to rapidly how changes in geometry or changes in inputs will change your results. Okay, I have a problem here with it's fine. Okay, let me get this. You can see this new geometry comes in, impacts the cylinder, and bounce off, creating a secondary dent, but in a different location. We can look at global data, and this is a very different looking kind of energy data. And reaction forces are listed on a graph at the bottom of the page, and you can see oscillate around significantly. Okay, so that's the end of my demonstration problem. What I'd like to open up a second poll, and I want to ask you if you think that this tool might be useful in your work. So open that up here. Take me a sec to bring that in. I open the poll, so I'll give you another minute to respond to that. Okay, those are coming in. I think most everybody answered. I'll give 10 seconds here. I'll close the poll. Results. And everybody thought that it would be at least somewhat useful, if not very useful. Okay. All right, just list a few conclusions about this product. Workbench Dyna combines the functionality and ease of use of Workbench, power of the Dyna solver, geometry, mesh loads, constraints, material properties, context settings, and analysis settings within the mechanical interface. It's also relatively easy to learn the tool if you're already familiar with Workbench and specifically Workbench Mechanical. So one of the other big advantages, if you already have a model set up as a static structural analysis, you can always just simply copy that system over to a Workbench LS-Dyna system, and then you don't have to create a new mesh. You do have to assign new loads because the application methods are different. The contacts are different as well, and the analysis settings are different. But certainly the mesh and the geometry would come over. Things like symmetry conditions would also come over to the Workbench Dyna analysis. Also, I do want to reiterate that the now post-process with this tool within the Workbench environment, so you don't have to learn another post-processor. Much. I am going to try and answer some of your questions now. Okay.